Hi everyone, Mr. Neighbor here, and we're still working on displacement and velocity. So the last problem we ended with in the last video had this graph to it, and it was talking about what's the distance this car traveled and what's the displacement of the car. So we estimated this location where the car is ending at to be about 3.75, and then we saw that it started at 0.5, so the distance it traveled was 3.25 miles. Oh, sorry, meters. The label of meters right there. Using significant figures, when we add, we're going to take the least precise measurement. So the least precise measurement would be the 0.5 to the 10th spot. So I rounded my 3.25 up to 3.3 meters. Displacement, that actually has a formula unlike distance traveled does, and the displacement is calculated by the final position minus the initial position. Blech, can't talk. Whew. So the final position is 3.75. Again, that needs to be meters, not miles. And the initial is 0.5 meters. Subtracting those, you get out approximately 3.25 meters, but we'll just say significant figures are important to us, not say they are. Sorry, that came out odd. But we're going to use significant figures with this, and that would round it up to 3.3. Notice I'm using the approximate sign because I did approximate this value right here. And as soon as I use significant figures, I do have an approximate answer already too. So let's try another one like this. Here we have another graph. It looks like the car is starting at 3.75 this time. It's ending at 0.5. So we're going to have pretty much the same problem going on. For our distance traveled, we're going to go the same amount of distance. It's still going to be 3.3 meters approximately. Nothing's changed. It's like this graph flipped. It did do this last time, and now we're doing what's in green. The displacement, let's look at the formula to make sure we know what's going on with that. So remember, displacement is calculated by the final position minus the initial position. So our final position this time is the 0.5 meters. Our initial position is the that should be a minus sign, 3.75 meters. And that's approximate, so I'm going to put an approximation dot above that. When I subtract these two, I get out negative 3.25, which sig figs will make negative 3.3. So notice the difference in this negative sign. That's the thing, that's the game changer. Displacement is a vector quantity, like velocity is a vector quantity. It has a direction to it, and the negative sign, that is the direction. It's telling us the opposite of what it was going in. So if it's positive, we assume to the right. It's negative, so we're assuming it's traveling to the left or backwards. It's going in reverse. So negative signs are important. This tells us something. It tells us the reverse direction. All right, let's transition now into speed and velocity. First, speed. Speed is simply a measure of how quickly an object is moving. So how much distance something travels in a given time. Notice we're talking about distance here, okay? Not displacement. So a swimmer travels one complete lap in a pool that is 50 meters long. The first leg is covered in 20 seconds. The second leg is covered in 25 seconds. What was her average speed for the lap? Let's talk about average first. We're looking for average speed. So what is an average? An average is the sum of all those things you have divided by how many of them that you have. So for us, we're talking about two different speeds here. We have the speed of one leg, so that's the first distance across, the first 50 meters. And then we have the second leg, the distance back. So it would be in the same lane, of course, but the arrows just show you this is the first leg and this is the second leg. So we're going to add those two speeds together and divide by how many we have, which is 2. So let's look at the first speed. So we're traveling 50 meters in 20 seconds. Notice that these numbers have 3 significant figures. So when I divide them and get out 2.5, I need to have 3 significant figures. So I have to put a 0 on there. So that's speed 1. Okay. Speed 2, when the person is going back, they're still traveling 50 meters, and they're now doing it in 25 seconds because they're tired. It's going to take longer. So when we divide that, we will get out 2. And I have to include those 2 zeros after the decimal point because I need it to be 3 significant figures because both of these were 3 significant figures. Now I have to find the average. So a lot of times when you see speed, it'll be written with an S, not to be confused with seconds. And there'll be a bar across the top. The bar across the top means average. So what I need to do is I need to take my 2 speeds, the 2.5 and the 2, I need to divide them by how many I have, which is 2. So I will get out 4.5 meters per second, and I must divide that by 2. Oh, there's my 2. And what I get out is 2.25 meters per second. So that is my average speed for this swimmer. Now let's look at velocity. Velocity is a vector quantity that measures how much displacement an object does in a certain amount of time. How fast that displacement is changing, or how fast their position is changing is how sometimes we think about it. So average velocity is equal to the displacement divided by the time. Notice here we have average velocity with that little bar over the top. It's talking about delta x, which is change in position, delta t, which is your change in time. So you take the final position minus the initial position, divided by the final time minus the initial time. Usually we think about this just as t, because we're looking at, over this many seconds, over 2 seconds, and then we just punch in a 2. A lot of times the calculation for TF minus TI is already done for us. So when we talk about speed and velocity, we need to remember what instantaneous means. Instantaneous means how fast an object is traveling at that time, because the speed or the velocity is probably changing. So a speedometer measures instantaneous velocity. For velocity, it needs to be a speedometer and then also a compass because we need a direction with that. So instantaneous velocities, they are at one single instant. Average velocities are over time. So a lot of times we don't know the in-between. We don't know what every single speed was at every little second. Or more importantly, you need every single speed at every instant in time, which you can't figure out. That means half seconds, quarter seconds, milliseconds, all those times. So we have average velocities. You'll see that a lot. What we're calculating is actually an average velocity, not the true velocity. So just be very, very careful about that when you're talking about things, the average velocity. And last, we have constant speed and constant velocity. That's when it's not changing at all. It's putting it on cruise control, or putting it on cruise control and not changing your direction or turning at all for velocity. So remember, velocity, if it's a constant velocity, you're not changing the speed and you're not changing your direction. You're holding straight. Also, resultant. This is a word that we use when we talk about vector quantities. Vectors are really arrows. So let's say you're going this way at 4 meters per second. And then the wind is blowing you north at 1 meter per second. Well, if the wind is blowing you a little bit, you're not going to go straight. You're actually going to go over this way more. So you have something called a resultant, which would be this dotted blue line. That's your true direction. It's the addition of both of those directions. So resultant is a combination of 2 or more velocities. And it doesn't have to be a velocity. We talk about resultant vectors with positions. We talk about resultant vectors with forces, lots of different things. But right now we're dealing with speed and velocity. So we talk about it with those 2 things. One example you can think of